Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we will continue our discussion from the previous module where we were discussing the rigid body planar motion. So now let us talk about the various principles. For example, the principle of angular momentum, the principle of energy and linear momentum conservation and so on. So now in planar motion, the issues are slightly resolved. Right, so the issues are resolved. So we see that the angular momentum has a constant direction perpendicular to the plane of motion, and this is the so-called axial angular momentum. The angular momentum has a constant direction perpendicular to the plane of motion, right? And we are only going to focus on the axial component or the axial angular momentum. So in that case, the angular momentum principle along the axial direction simplifies to the following form: d dt of L naught n is k naught n. So n is our direction perpendicular to the plane. So perpendicular to the plane, to the plane of motion. Okay. So then, the second part of the second equation is that we have, due to the rotation of the object, we see that the change in what we can do is, this is not a different equation, we are just rewriting the first equation here. So what we see is that we are rewriting the angular momentum. So we have I naught omega times n bar is k naught n. So that's the rigid body equation, and typically I naught being the moment of inertia of the object, it's going to be a constant, and we see that we get I naught times d omega dt is equal to k naught. Okay, so that's the equation governing the rigid body. And further we so this is the rotational part. Further we know that the center of mass may also move of the rigid body. So we will have separate equations governing the center of mass, namely the planar rigid body equation. And we see that this is m times dv dt fx and m times dvz dt, which is fz, right? And we see that this is the case. Okay. We are talking about, we have the x direction and we have the z direction, and we are talking about the center of mass here. So these are my center of mass equations, or the equations governing the translational motion. Okay, and then so what we see is, now for rigid bodies the setup is more complicated. We don't have just the translation but the rotational part. So we have more equations than a simple body which is not exhibiting rigid body rotation. So we will have to solve all these equations, all these three equations, to find out the motion of the rigid body, equations governing rigid body motion. Okay, equations governing rigid body motion. So let us now look at an example. So suppose we have a circular pulley. Suppose we have a circular pulley of mass m, right, and radius a. Suppose we have a circular pulley of mass m and radius a, and it smoothly is pivoted about an axis. Smoothly pivoted about an axis, let's say O comma J, right? So here is this, we have a rigid body which is smoothly pivoted about an axis. Let's say we have the axis, so we have a mass capital M which is pivoted about a pulley, and the pulley connects the mass with a string which is a light inextensible string. So typically we will have a tension in the string so that the string is not slack. So let me write this statement: a light inextensible string is wrapped around the pulley, so that it does slip, right? So there is some sort of a slippage involved, and the system undergoes planar motion. The system undergoes planar motion, and we see that, well, planar motion with the particle moving vertically. Okay, so I think the setup is fairly clear. There is a pulley mass system. It is a planar motion, so the axis of rotation is perpendicular to the plane containing the motion. So that's my axis of rotation, and then we have to find the downward acceleration. Find the acceleration of the particle, of the particle. Okay, it is so the particle is of mass small m, the pulley is of mass capital M, right? So we see that the forces which are acting on the system are the respective weights and the tension in the string. The weights will all act downward, so we expect the entire system to go down, so the acceleration direction will be downward. That is fairly clear. Now let us draw write down the various equations of motion. So we note that not only the system is translating, the system of the pulley and the masses, but also the pulley is rotating. So we have to write all these equations here. So the force balance we see that for the particle m dv dt is mg minus t, and then for the pulley we see that so this is my force balance here. This is for the particle, so m dv dt is mg minus t, and for the pulley we see that the pulley is rotating, so we see that I naught d omega dt is a times t, which is the net moment. So this is my moment k naught, right? Now I naught, so notice that the pulley is a disc. Well, it's not written, but it should be fairly clear that the pulley is a disc. So we have that I naught has to be half m a square, the moment of inertia of a disc, right? So we plug it here, and further we have that omega is V over A, well, it's given that the problem does say that the pulley mass, the string is wrapped around the pulley, that it slips, but the system undergoes planar motion. So the moment we have a planar motion, we expect that there is no component of motion out of the plane, which means that omega has to be obeying this relation. Omega is V over A. We plug all this information and we find that we can eliminate this tension T in both the equations. We find that the acceleration dv dt comes out to be 2m by 2m plus m by g, right? And that is well, I think the problem, well, I need to be very careful. The problem says so that the pulley does not slip. I think that is crucial, because the moment there is no slippage, then this is the no slip condition. Omega is equal to V over A. So does not slip, no slip condition. So that is how we are able to solve the problem, by eliminating omega and T. Okay, so then let us look at one more example of this two body system. This next example is fairly popular in children's circus, where the circus performers tries to balance along very difficult terrains, like for example rope or a ball or something, where he or she tries to balance their weight in and goes and walks in such a way such that it is against against their regular weight, against their action of the weight, so that the entire system is stable. So we will look at the mechanics of such an acrobatic tricks, the example of such an acrobatic trick. So the problem is related to a circus trick. So what the problem says is that we have a performer. Let's say we have a performer, let's say a man or a person which is standing on a ball, and in such a way that he or she doesn't fall. And in doing so, the man is going to move, and in doing so, the ball is also going to move, right? So suppose the man moves forward, the ball is also going to move, and such that, well, the man has to move backward. Sorry. The man moves backward so that the circle moves forward and the net system is stable and the man doesn't fall. So that is the whole idea. So a performer of mass m, so that is the mass of the object, the man which is standing, causes a large ball of mass m and radius a to accelerate to the right. Right, by running to the left. The ball accelerates to the right and the man is running to the left. So now on the upper surface of the ball. So then the problem says, well, the man does not fall. The man does not fall, because what happens is, he is going to maintain this motion in such a way that the angle alpha remains constant. The angle alpha being, so let me complete this statement and I'll draw the entire diagram. So the man does not fall because he maintains this motion in such a way that angle alpha angle alpha remains constant, and then we need to find the necessary condition. We need to find the necessary condition for such a motion. We need to find the necessary condition for such a motion, and let us set up this. So we have the ball with center O, and then we have the mass of the ball which is acting downward, and then the man is standing on the ball, but it is going to the left, such that this angle alpha remains constant. And then so we have the mass, and of course the ball is going forward, so it is going forward. So there is some, is it given that the ball is not slipping, it is rolling? Nothing is given. So we can assume the ball is slipping and it has some friction force, let us say F1, and of course there is a normal reaction of the ball which is N1 perpendicular to the ground, and then of course the man will exert a normal force N2, and it is, since it is going to the left, it will have a slippage F2, right? So that is the ball man system, and we have to find so this is what we have. So let us draw this diagram separately on the man, the force diagram. So what we see is that here is the man which is standing on the ball, and this is subtending an angle alpha here. So we expect the man to have a weight, also to have a weight mg, so mg acts downward, and we see that the normal reaction, well, so what we have shown was earlier was the ball man system, so the normal reaction was acting on the ball. So here we have shown the forces on the ball, and now in separately we are now showing the forces on the man. So by Newton's third law, since N2 was acting towards the ball, N2 will act away from the ball on the man. So they are equal and opposite. And similarly, F2 will have this component which is equal and opposite to F2 on the ball. Well, we don't know where F2 is acting. F2's direction is also unknown, so we may reverse the direction in both the cases. The answer is eventually given by the math of the problem, right? So then what we have is that since this is the case, this is also going to be alpha, and this is also going to be alpha, right? And now we are quite ready to write the force balance on the ball and on the man. So so what we have is, most important is both the ball and the man, they are accelerating with the same linear acceleration dv dt, right? So both the man and the ball, they have the same acceleration which is given by dv dt I hat, and we see that the force balance for the man will have, the force balance for the man will be of the following. So we have along the radial direction, we see that m dv dt. So we need to have one component along the tangential. So n2 will be, and so this one is n2 sine alpha, and so the force balance along the tangential direction. So this is tangent, right? So m dv dt is going to be n2 sine alpha minus what are we doing? I think something is not right here. So this is my n2 sine alpha, right? So this is along the x direction. So we are writing the force balance along along the two coordinate axes. So this is along the I hat. So n2 sine alpha minus f2 cos alpha, and then Similarly, along the j hat, so we have I hat this direction and j hat is this direction. So along this direction, we see that there is no net acceleration, and we have the reaction forces. They are going to balance the weight. Okay, so this is for one object, and similarly for the other object, the ball, we can write a similar. So now the ball is rotating here. See, the man is a point object, the ball is a rigid body, so the ball will not only experience translation but also rotation. So we see that the force and the torque balance, the force and the torque balance is m dv dt is f1 n2 sine alpha plus f2 cos alpha, right? And we see that this is 0 is n1 minus mg minus n2 cos alpha minus f2 sine alpha, right? So these are the force and the torque balance on the ball. Okay, so this is the force balance along the I hat direction, this is along the j hat direction, so the diagrams can be seen. And then we have the torque balance, which is given by I naught d omega dt is af2 minus b minus af1. So f1, notice that f1 is moving the ball in the anti-clockwise direction, and f2 is moving the ball in the clockwise direction. So hence the net torque will be af2 minus af1. So then we can solve all these to find that all these equations. See, the unknowns in the problem are f1, f2, n1, n2, 4 unknowns, and also I naught. We don't know what is the ball. The ball is not given as such. It could be a hollow sphere, it could be a rigid sphere, we don't know. But I naught itself, well, I naught itself is an unknown of the problem. But the other issue is omega. So what is omega? We cannot have, see, I naught is an unknown. We have 4 unknowns, n1, n2, f1, f2, 5 unknowns I naught. We cannot have a 6th unknown because the number of equations are 5. So omega, we can apply omega to have the rolling conditions. So omega is v over a, and then we will get our acceleration of the system dv dt is mg sine alpha. After solving all these 5 equations, we get that this is m plus I naught by a square plus m1 plus cos alpha. Okay. Okay, so then I think that explains this problem. And then the next set of examples that I have is related to the 3D statics, right? Again, the motion involving the equilibrium setup of an object which is kept in 3D space. We have to analyze the various torques and the forces and try to eventually find out the various quantities asked in the problem. So let us see some examples. Again, this will be an example of the rigid body motion, but in 3D. So we are talking about rigid body statics in 3D. So we assume we are talking about the statics of the body, which means the body is not in motion, which means of course there will not be any acceleration, there will not be any moments. So the net moments, they will balance, the net forces will balance. So what happens is, in this setup we assume the body in equilibrium, under a 3D system of force, and we take care of zero net forces and moments. So this is a statics problem in statics. So we have no forces, no moments in this setup. So we just calculate the moments, we write down the moment equation, we write down the force balance, and we set it equal to 0, and from there we find the unknowns. Okay, let us continue our discussion by looking at some examples in 3D statics. So the first problem is that we have a rectangular plane. So in 3D, so we are talking about an object in 3D. So the object is a plane, and the plane is kept, the plane is kept. Let me write the statement, that will be clearer that way. So we have a rectangular plane, A, B, C, D of mass m is placed, a rectangular plane mass m is placed with its edge AB on the rough horizontal floor. On the rough horizontal floor, z is equal to 0 with the vertex D. On the rough horizontal floor with the vertex D resting against a smooth wall. X equal to 0. The four vertices of the panel are at points. The four vertices of the panel are at points A, which is 2, 0, 0, B, which is 6, 4, 0, and C, which is 4, 6, 6, and D, which is 0, 2, 6, respectively, right? So this is where the panel is kept. So we have the first point. So if we draw the diagram here, we have the x-axis, we have the y-axis, we have the z-axis. The first panel D, the point D is resting along the XYZ plane. So here is what we have D. And then A is 2, 0, 0. And we see that A is this. And then we have B. B is given by 4, 6, 4, 0. And we see that the point C is in 3D space, which is given by 4, 6, 6. Okay, so now the problem says, given that the panel is not slipping, given that the panel does not slip, we need to find the reaction forces exerted by the wall and that's it. So the reaction forces exerted by the wall. So then what we see is that so what are the, we need to see what so reaction forces exerted by the wall. So here we see that the rectangular panel is resting, so the wall is along the xz direction, right? So and the rectangular panel is resting only at one point on the wall, and so we expect the reaction force to be perpendicular to the wall. So the reaction force is along the x direction, because the reaction force, the wall is at the yz plane, right? So let me call the reaction forces as N. And now let us find what are the different forces acting on the object. So the different forces are, of course, the wall reaction given by N of I, and we have the weight which is given by minus mgk, the weight which is mgk, which is now acting, of course, acting downward, so mgk with a minus sign. And then we also have the reaction forces by the floor. So we have CD, and then we have the point B and the point A. So the reaction force by the floor, the reaction force by the floor, and we have which we can assume that this is exclusively at points A and B, exclusively at points A and B, right? Let me call these reaction forces are as X bar and Y bar, and we see that, so we have four unknowns. Well, we have four forces and we have three unknowns, N, X and Y. We are assuming that the reaction forces by the floor are exclusively at the points A and B, right? We can certainly assume that. Now, there are just too many unknowns of the problem. See, we have to write down the moment equation. So in 3D, there will be three moment equation along three directions, and we will have the net force balance. So we have three force balance. So we have six equations, but we have seven unknowns, three of the component of X, three of the component of Y, and one of the component of N. So we have to choose wisely our axis of rotation such that some of the unknowns get cancelled and we are able to find the problem at hand, which is the wall normal reaction N. So I think I am all out of time for this module, and in the next module we'll discuss the solution to this example. Thank you.